Well, good morning. This is Thursday morning, the 6th of July, 2017. It's already 8:10 in the morning. I've been sitting here waiting for my computer to boot up. It took forever. PowerPoint to open, that took forever. And then for the Screencast-O-Matic, which should have been open, but it was closed. It had gone to sleep overnight and shut down completely, so I had to boot it back up. But finally I got all that done, and still nobody is in the class but me. So wish y'all were here. It's quite lonely in here without you. So hopefully someone will be coming in soon. I did want to make a couple of announcements. In case you're wondering, I can't remember if I told you this before, but a week before last, I was named to be on a biology screening and search committee for a new biology instructor, which is pretty much a pain in the neck with my schedule this summer. But, you know, so they called for, now this was not this past Monday, but the Monday before, they said we could come by the Human Resources office on the Birmingham campus, of course, to screen applicants. And they gave us 2 times on Monday. I said, I can't possibly go on Monday. I have classes from 8 o'clock in the morning till 9 o'clock at night with 2 20-minute breaks and 2 10-minute breaks, and that's all. So I can't get over there and screen. So I said, can I do it Tuesday after 3:30, because that's when my second class ends here. I could get there by 4 o'clock. And they said, well, sure, if it's all right with Human Resources. So I did. Got over there, and Human Resources said, well, you didn't have to come. It's all online now. It never has been before, but they've got this new system in. It's all online. So there I wasted 30 minutes driving when I could have been in my office screening right then, except for the fact they couldn't get me logged on. The system was having difficulties. So I sat for another very close to an hour, 45 minutes to an hour, while they were trying to get me logged on to the system. And finally, when they did, then the secretary over there had to leave at a certain time. So I only got like 3 people screened out of something like 18 or 20 or 22. I don't remember how many applicants. I only got about 3 screened. And of the first 3 I screened, I differed from what the rest of the committee had done the previous day on 2 out of the 3. So it was not a good start to it. So anyway, she said, the secretary said I could take them home with me because it was all online anyway, take home the paperwork and do it at home. So I did that. That was a week from last Tuesday, the last Tuesday in June. I took them home. I got some screened that evening. Then Wednesday, of course, solid 8 to 9 classes, 13 hours plus. Actually 13 and a half hours a day on Wednesday, so I couldn't get screened any then, nor at home, because I got home close to 10 o'clock at night, so no screening then. So then Thursday, I screened just about all of my office hours Thursday. So I had done it on Tuesday. From 3:30 on, I had been screening, and every bit of office hours I had on Thursday when students weren't coming by. A few students did come by for registration and stuff. But except for that, I was screening nonstop almost, and took them home again. And over the holiday weekend was screening, much to my wife's chagrin. And so I finally got them done over the weekend. And then I got to starting on the papers, on grading papers. Of course, I had a whole week's worth of papers by then that I hadn't had a chance to grade at all. So I did that the rest of the weekend. Grading papers, got all of them graded, but, and here's the big but, I didn't have a chance to put them on Blackboard. So if you're looking for your grade, come see me. I'll show you your grade. Hopefully today, hopefully I have some office hours. I've already, a student caught me in the hall yesterday. I was leaving the classroom to set up a lab. I said, look, I'm in the middle of class. He was wanting advice on registration. And I said, any of these instructors can help, and one of them said, yeah, I've been helping him, but he had a question I couldn't answer. So he said he was coming by today. So I know I'm going to probably have at least 1 student come by, maybe more, but I'm going to try to get as much. I got another whole stack of grading to do from yesterday's 4 classes. So I will grade first, then put on Blackboard, then do attendance, and hopefully between 10 and 12 and 3:30 and 5:15, I will get most of that caught up. I don't know if I'll get it all. I'll take more home with me this weekend and try to catch it up then. Now, all that being said, that just explains why your grades aren't on Blackboard yet. Everything that's been turned in before yesterday has been graded. Here's the other flip side to that sad saga, is that the screening committee, we're going to be interviewing candidates. And they're going to set aside a day sometime, and I've requested repeatedly, please don't do it on Monday or Wednesday, because I am stacked with classes on Mondays and Wednesday. So that, if they listen to me, that means they'll probably schedule them for a Tuesday or Thursday. Hopefully only on one day. I think my last count was 9 candidates, one of which I thought should not be a candidate, but the chair of the committee thinks she should be, because she had 1 year teaching in high school and 2 years teaching in 7th and 8th grade science. No college experience, and that's in the things, or secondary, only 1 year of secondary, but she says 7th and 8th grade counts as secondary, which I've never heard that before. So anyway, we've got 9 candidates to interview. Hopefully some of them will say, no, we found another job, or no, we're not going to interview, or something. But hopefully we can get those all done in one day. And if they listen to me, it's going to be a Tuesday or Thursday, so that means we'll probably miss another class, okay? But I've got all the classes recorded from previous terms, so I think you can continue with what we've been doing. Just listen to it online. Sorry about that, and then too, they may schedule for Monday, Wednesday, so we may not miss any more classes. Anyway, let's get going. We were working on example 3 last time, and I don't think we finished it. I believe I was told, yes, let me work on it over the break, and if I have questions. So I put a question mark by it, but since nobody's here to see if you have questions, I'll go on and continue with this one. Here is by the way, we're in Chapter 2, First Order Differential Equations, 2.4 Exact Equations, top of page 68, example 3. Okay. Here is example 3, dy dx. I'm pretty sure we started this and probably got it mostly done, is equal to xy squared minus cosine x sine x divided by y times 1 minus x squared. Okay? And this is an initial value problem, so y at 0 is given to be 2. Okay? Now, taking a look at that, obviously not a linear differential equation. Okay? I believe with a little bit of study, you'll see it's not separable. Okay? Not autonomous by any means. Not linear. So right now our only hope is for it to be exact. So to get it into a form so we can consider whether it's exact, we're going to multiply everything on this side, on both sides, by that denominator, y times 1 minus x squared, y times 1 minus x squared, and we'll just do that for now, okay? So this will be, and write it in differential form also. So basically take out the dx here and put the dx over here. Okay, this part disappears, so what we have now is y times 1 minus x squared dy is equal to xy squared minus cosine x sine x dx. Okay, so that's your form for an exact differential. Is it though? We need to see. What's our test? We take the partial of this with respect to x. Well, let's see. The other thing let's do is let's write it into, get everything on one side. Now, it looks easier to me to subtract this from both sides and then flop sides. So I'm going to write it this way. xy squared minus cosine x sine x dx. And rather than put a minus, I'm going to put a plus y times, and reverse these two, x squared minus 1 dy. Okay, that is now, and this is equal to 0. And here's Marcus. So good to see you. I'm tired of talking to myself. Okay. Today is the 6th. Marcus is present. Okay. Projector, turn it on. Turn it on from the deep screen here. Since you are here, you may not go back and listen to the first part of the recording, so let me repeat it for you now while that's coming on. I don't know if I told you last week or not, but I've been named to a biology screening and search committee. They did that the week before last. And they had set up 2 times on Monday of last week, not this week, for us to go to the Human Resources Office on the Birmingham campus to screen candidates. They had a whole, 18, 22, something like that candidates, a whole passel of them. Okay? Well, the 2 times on Monday I couldn't do it because I'm in class from 8 o'clock in the morning till 9 o'clock at night with 2 20-minute breaks and 2 10-minute breaks. That's all. Okay. And I said, I can't possibly do it then. Could I come Tuesday afternoon after my 3:30 class is over with? I can drive over there, be there around 4 o'clock, and screen for the rest of the day. They said, sure, if it's all right with Human Resources. They said, sure, come on. So I got over there, and they said, well, you didn't need to be here. I said, what? And they said, yeah, it's all online now, which they've never done before. I've been on many screening committees before. The first time it's been online. I said, well, why did you make me drive over? Well, I don't know. So, anyway, there I lost a half hour driving. Well, as it turned out, they couldn't log me on anyway. So it took 45 minutes to an hour for them to find a way to get me logged on. The system was having difficulties. It's a new system for us anyway. So when they finally did that, by then it was close to 5 o'clock, and the secretary had to leave by 6 or 6:30 or something like that. So she had to lock things up. So by the time I got going, I only had time to screen just a few candidates. And she said, but it's all online, so you can take the paperwork home with you and do it at home. So I did that Tuesday night. That was last week. And then Wednesday, of course, in class all day long. Had no time for screening then or at home because we got home around 10 o'clock. So then Thursday of last week, every spare minute I had was screening candidates. I had no time to grade, no time to do anything except screen candidates, except, of course, I had students coming in to register and that kind of stuff. So I had to take care of them, too. So I took them home with me over the holiday weekend, and I screened when I could. We were out of town, so it wasn't always easy to, but I screened until I got them all done and got emails done and that kind of stuff. Then I started grading papers. Now I had a week's worth of papers, okay? For 6 classes, that's quite a few. Yours was one of them. And I finally got everything caught up with grading, but I didn't have a chance to put it on Blackboard. Okay, so your paper's graded, but it's not in Blackboard yet because I just ran out of time. And today is hopefully I'll have sometime between 10 and 12 and sometime between 3:30 and 5:15 when I'll have some chance to get some. I got this much new grading yesterday, so I've got that much to grade, and then get everything in Blackboard, the attendance caught up, and that kind of stuff. So I don't know if I'll get it all done today, but I'll do my best to get as much as possible. And then I'll take it home over the weekend and continue working on it. Looks like a much nicer weekend than we've had, so I count on it raining some so I can get some stuff done, but when it's not raining, I'm outside working. So we'll see. I'll try to get everything caught up as much as possible today and anything else this weekend. So hopefully that will be done. The other side to that coin is we've still got interviews to do. I think we're down to 9 candidates. Really, 8 of them I think are viable. One of them, for some reason, the chair thought 2 years teaching 7th and 8th grade science was adequate for the 3 years experience they needed. And it said secondary or post-secondary. To me, that's not secondary or post-secondary, but she said it was okay because in some places they allow 8th grade. She taught 7th and 8th grade. So I don't see how it is. She's never taught a college class in her life, and yet we have to interview her. So I think we've got 9 interviewees. Hopefully some of them will say, no, we've already got something else, and no, we don't want to come, or something like that. But we could have as many as 9 show up. And if they do it on a Monday, Wednesday, then I'm in really bad shape because I'll lose another Monday or Wednesday of class. So there's a chance if they listen to me that I'll do it on Tuesday, Thursday. So if they do, we may miss another class here. Hopefully we'll get it all done in one day and not in 2 days. Okay. Perfect attendance today. Good to see. Okay. Y'all are finally talking again. I was commenting to Megan that for the last 1, 2, 3, 4 classes, only one of you had been here, and y'all alternated on who was here. So I thought y'all didn't like each other anymore, or you just both couldn't stand being in the same room with me. I don't know what it was. Okay. I was just telling Marcus, and she may not go back and listen to this. Sorry, I have to go through all this again. I think I announced to you a week ago, when we were last here, that I was on a screening committee for biology. And they wanted us to go over and screen on the Birmingham campus, of course, Monday of a week ago. Not this past Monday, there was no school, but a week ago. And I said, look, I'm in classes from 8 in the morning till 9 in the evening with hardly any breaks. Can I do it Tuesday after 4? Because I'm in class until 3:30 and it'll take me a half hour to drive over there, or allow a half hour. And they said, well, if it's okay with human resources, they said, sure, come on. So I went over there, and then they said, well, why are you here? You could have done it online. They've never done it online before, so this is the first time I've had the experience of doing this. I said, well, I just wasted a half hour driving over here if I could have done it from my desk. They said, well, we don't know why. They didn't tell you. So anyway, then they tried to show me how to log on, and it wouldn't log me on. So then they had to go through all sorts of stuff, calling people, emailing people, back and forth. Finally got me on about 45 minutes to an hour later. I couldn't look at a thing because it's all online. If they had them in paper copy, I could have been at least screening them then. They didn't. So finally they got online, and then by the time the secretary had to leave, I only had time to screen like 3 candidates. Okay. And of those 3, I disagreed with the other committee members on 2 out of the 3. So I said, this is not looking good. And then, so she said, well, since it's online, you can take the paperwork home with you and do it anywhere you want to. So I did, and I screened that evening, much to my wife's chagrin. And then Wednesday of last week, I was in class all day, so I couldn't screen any then. Thursday, every bit of office hours I had. It happened on Tuesday after 3:30. Thursday, every bit of office hours was spent screening, except when students came in to register for fall, which several did. But anyway, I still didn't finish, so I took it home with me and screened over the holiday weekend. And we were out of town, so I didn't have lots of opportunity to, but I finally got them all done. And then, by that time, I had a week's worth of grades that I hadn't even touched yet. So I finally got all those graded, but I didn't get them on Blackboard. So I was just telling Marcus that things that were turned in by last week are all graded, but they're not on Blackboard. So I'm going to try to do that today, except I got this many more papers turned in yesterday. So I've got those to grade, plus the everything on Blackboard and attendance. And I don't know if I'll have time in my 10 to 12 today and 3:30 to 5:15 today, but I'll do as much as I can. I'll take the rest of them home with me and work on one over the weekend, much to my wife's chagrin. Okay. Now, the other side of that is that we still have to interview. We're down to about 9 candidates. One of them I don't think is viable at all, but the committee chair insisted we keep her. She's had 2 years experience teaching 7th and 8th grade science. And I don't think that's adequate for teaching college biology. But the chair did, so we're going to, I guess, interview her too. So we got 9 candidates. I've said I really can't afford to do a Monday, Wednesday because I'm in class all day. So whether they listen to that or not, I don't know. But Tuesday, if they do it Tuesday, Thursday, we'll probably lose another class. Tuesday or Thursday. Hopefully we'll send them all in one day and won't lose 2 days of classes, okay? But I can't control that at all, so. Anyway, that's where we are. Sad, sad song, isn't it? Okay. You were here last Thursday. We were working on example 2. I don't think we finished it. And I think you said you would try to finish it. And it was going to be, if you had any questions, we would deal with them. Did you? Did we want to pick up where we left off, or what? That's the example. I started with nobody in here, so I just started doing it over again. What's that? Okay. All right. So here. Right. Okay. Well, this is Chapter 2, First Order Differential Equations, Section 2.4, Exact Equations. And this is an initial value problem, example 3, top of page 68. And I wrote it down. I wrote it in differential form. Then I moved this. I moved this term over here and subtracted this term here. But rather than put a minus sign, I reversed the order of these two. So that's the same thing. Just subtracted it over there. Now it's in exact equation form, but what do we have to do here? We don't know if it's an exact equation until we do the test. And how does that test go? This, remember, they typically call your m of xy, and this one they typically call the n of xy. Okay, what do we do with those? Now we take a partial of this one with respect to the m with respect to, no, the other one, y. Yeah. So let's do the partial of this one with respect to y. Okay. I'm not going to write it down. You tell me what that is. Partial of this thing in parentheses, this m of xy, with respect to y. To xy, exactly. You count all the x's as if they're constants, and so that's just a coefficient of the y squared. The partial of xy squared with respect to y would be 2xy. Okay? This term has no y dependence on it, so that's treated as a constant. The partial of that is 0. Okay? Let's do the other one, and this one we do partial with respect to x, the opposite of that one, of this thing in brackets here. And what does that give you? It might be beneficial to write this as x squared y minus y, if that's helpful to you. Take the partial of that. With respect to x, say again? Take it with respect to x. 2xy. And that term is a constant, so the partial is 0. Yes! It fits the bill. We have verified this is an exact differential equation. So, in order to save space, I'm going to erase what we just did. All that was your test. Oh, no, I hit the wrong key. Yuck, and it won't go back. Let me see if it'll go back. No. I can't get it back. Okay. All right. I can't get my pen back. There we go. All right. So let's write it down again. That's xy squared minus cosine x sine x dx plus, I'm sorry, get the right key now. Okay. Y times x squared minus 1 dy equals 0 when y of 0 is equal to 2. So y not a g. Okay? So there's our problem. We know it's an exact differential. What's our first step here? Yeah. Okay? And which one do you want to do? Okay. So, okay. Okay. Let's, okay. There's a little subtle thing here, and they don't really phrase it too well, but the function that we're looking for, okay, and if you go back to all right, no, that's still not it. When they first introduce, okay, now we are assuming, because it is an exact differential, there is some function f of xy equals c. Okay? That's our assumption. There is some function f of xy equal to some constant c. And if you do that, then you take a partial with respect to x, and that would be partial of f with, and that's going to be our solution, by the way, okay? Partial of f with respect to x dx plus the partial of f with respect to y dy is equal to 0, okay? Because partial with respect to c. So if that's a solution, then we're going to try to match this up. Okay, so that means, see, here's our dx, there's our dy. So that means the partial of f with respect to x is equal to xy squared minus cosine x sine x. Okay? That would be what that's saying. This is what we integrate. Okay? We integrate this, we just get f. F is a function of x and y. Okay, when we integrate this, and we'll do our dx over here, basically take out the dx there. Okay, integrate that with respect to x. What would that be? Integrate that with respect to x, meaning you count your y's as if they're constants. Just integrating with respect to x. What would that give you? Say that again now. Okay, you treat y as a constant. You're integrating. So just imagine this. Name a constant. Maybe not, we've argued it. dx. No, let's not use d. Okay. F. No, not F. E. Okay, how about E? No, that's exponential. G. will be px, integral of px dx, where p is just the number. Say again? Well, integrate that. Over 2. So it would be px squared over 2. Well, that your y squared is your p, so that would be x squared y squared over 2. Right? Okay. Undo that. Take the partial of this with respect to x. You get 2. The 2's cancel out. X y squared. Yeah, that's right. Now, integrate that with respect to x. Okay? What's that? Okay. You could either do sine or cosine. I'm real tempted to do cosine. Okay. Now we're integrating this, so let's just do these separately. Okay. Now, if you this is a substitution, right? So let u maybe, I think that's safe, equal cosine x, then du is equal to minus sine x dx, right? Derivative of the cosine is minus sine. That's why I chose to do the cosine, because that will take care of the minus sign. So that would be, and then what we have then is the integral of u du, okay, with that becoming a plus. Well, what's the integral of u du? U squared over 2, okay, where u is cosine, so that'll be plus cosine squared x over 2. All right? Now, I think typically at this point, we do not introduce your constant coefficient as per se, okay? But what we do is, because we're integrating with respect to x, that could introduce a function, let's call it g of y. That's going to be our constant of integration. It could be a constant or it could be a function of y. Because we're integrating only with respect to x, we wouldn't have noticed the y's anyway. So that's equivalently a constant. Okay? Now, so we've undone this one. Now let's take this proposed solution and do the partial of this with respect to y to see if we can make it look like that. Right? So let's do that then. The partial of this f with respect to y would then be what? Two x squared y, perfect, because you take it with respect to y now. Okay, and what happens when we take the partial of cosine squared x over 2 with respect to y? It's all a constant, so that's 0, and this gives us plus g prime of y. Because to take the derivative of that, that's a pure derivative, right? Now, we go up here, and again, here is where I suggest it's probably beneficial to write this as x squared y minus y, right? Distribute the y across the parentheses. Well, let's see. I'm sorry. No, that's right. This is supposed to equal that, right? It doesn't quite. I mean, it's close, but no. Wait. There is no 2 there. Sorry about that. It's 2y, but it's to the 1/2, so the 2's and 1/2 cancel out. So it's x squared. So these two are perfectly matched, and this tells us that dg dy is equal to minus y, right? So let's integrate that one. dg is equal to minus y dy. G's and y's look very similar. This gives us g of y is equal to, what would that integrate as? Help me, help me. Integral of minus y dy. Minus y squared over 2. And there we have our plus c, finally. Okay? So let's plug that back in to our f here. So your f of xy is equal to, now let's see, let me make sure. They approach this a little bit differently from what I have. But let's go on with it. We can leave off the c for now because we're going to bring it back in later. Okay? So this is x squared y squared over 2 plus cosine squared x over 2, and the g of y is minus y squared over 2, and this is equal to c. Okay? There's our constant. Now, guess what? We can multiply everything by 2, can't we? And write that as, because that would just make a new constant. So let's rewrite this as x squared y squared plus cosine squared x minus y squared is equal to some constant c. Now what do we do at this point? Plug in your initial value. The x is 0, that goes away. Cosine of 0 is, and by the way, please folks, I think you've been in calculus long enough to know, if you ever see a trig function in calculus, what mode are you in? Radian mode, never degree. Wouldn't matter here, but be sure you never are in degree mode in calculus, okay? So when you plug in a 0 for x, what's cosine of 0? 1, and 1 squared is 1, so this becomes 1, minus 2 squared, which is 4. This is equal to c, so c is equal to negative 3. So your solution is x squared y squared plus cosine squared x minus y squared is equal to negative 3. There is your function that satisfies that differential equation. Okay? Let's see how the book did. They said, okay, they reversed everything, okay? They made it, they negated this, that, and that, okay? And rearranged the order and made it y squared minus x squared y squared minus cosine squared x is equal to 3. Same formula, same equation, okay? Except the only thing they did here was make this y squared times 1 minus x squared minus cosine squared x is equal to 3. Okay. That's how they finally wrote it. Y squared times 1 minus x squared minus cosine squared x equal 3. Came up with the same answer. Guess what? They approached it differently and still came up with the right answer. Okay? So it really doesn't matter which way you go. What they selected to do was to do this one first and integrate that and then plug in the other. It doesn't matter. It doesn't matter at all. You should get the same answer. All right. Now, in your book, and I see one of you has a book but not the other. Oh, okay. All right. If you did a graph of that with equal to c, this would be the graph that you come up with. When that c is equal to negative 3, there would be the one particularly specific solution where y of 0 is equal to 2. That would be the curve that you would use. So you see, you still get a family of solutions, but the initial value tells you which one to choose. Okay? Now, I'm sure you remember fondly integrating factors, don't you? It's how we solve what we call linear differential equations, where it was set up to be a linear equation, do an integrating factor. Well, guess what? That was in section 2.3. Recall from section 2.3 that the left-hand side of a linear equation, when it's written, now I'm going to erase this, is that okay? This time I do want to erase it all, okay? Okay. If you have the linear equation y prime plus p of x, y is equal to some f of x, okay, that's a linear equation in y, because your y prime is to the first power, your y is to the first power, and everything else are x's. No coefficient here for the y prime, or coefficient of 1, some function of x, coefficient of y, and then some coefficient of x, some function of x is on the right-hand side, okay? That is your typical linear equation, okay? And that can be transformed into a derivative when you multiply by an integrating factor. The same basic idea sometimes, oh boy, key word there, sometimes works for non-exact differential equations, where you have m of xy dx plus n of xy dy equals 0. If you have that form, but it doesn't meet the test. That the partial of m with respect to y is not equal to the partial of n with respect to x. So it's in the differential form, but it's not exact. Well, what if we could come up with an integrating factor that made it exact? Okay? And they named that mu, just like they did before, the integrating factor of mu of xy. Okay? And what we want to do is multiply this by both sides of the equation. So it would be mu of xy, m of xy, dx, plus mu of xy, n of xy, dy equals 0. And if you did that, and then when you did the partial of this product with respect to y and the partial of that product with respect to x, okay, and they came out being the same, then you managed to make it exact, okay? And by the way, you multiply by mu by 0 too, but it just came out 0, okay? If you can make that an exact differential, then you now can proceed with what you had before. So in an attempt to find mu, we turned to the criterion 4 for exactness, and that was the one that the partials have to be the same. That's back on the bottom of page 65, that the partial of n with respect to y has to equal the partial of n with respect to x, just like we've done before. But now we have the partial of mu m with respect to y has to equal the partial of mu n with respect to x. So this is our criterion now. Now, are you familiar with the subscript notation for partials? We've been writing the partial symbol, but this is another way to write that. So if that is met, then you're okay. Okay? Now, if that is met, that means remember, partials follow the same product rule form that regular derivatives does. How do you do your product rule? You tell me. Okay, so that would be mu sub y times m plus, second, mu times m sub y, okay, right, is equal to mu sub x times n plus mu times n sub x, okay? That would be how you would take your partials of both sides, okay? Now, if you get your partials of mu on one side and your non-partials of mu on the other side, what do you have? This would be mu sub y m minus mu sub x n is equal to move the mu's to the other side, and that would be n sub x minus m sub y mu. Okay? Now, the only trouble is they do it the other way. So to be consistent with them, we'll do it. We'll just reverse sides here and change the signs again. So that'd be mu sub x n minus mu sub y m, you reverse those signs, is equal to m sub y minus n sub x mu. Okay, just to get it the same way they do. Okay. Now, they note here that m, n, m sub y, and n sub x are all known functions of x and y. You can do that. You know, you've already done it. In fact, you did your m sub y when you first tested that. Remember? You did your n sub x when you first tested that. You already have those. You know what m and n are because that was given in your problem. So you know all that. All that you don't know is mu and the partials of mu. Okay? So what you have to do is determine mu from that. Okay? So you have to solve a partial differential equations. Since we are not prepared to do that, have you had partial differential equations yet? I would think not if you're just an ordinary now. I've had it. Say again? I said, I think this is the hardest stuff. Right, okay. So you probably won't take partial differential equations. Count yourself lucky. I mean, they're not impossible, but they really are a lot more involved. So since you don't have the tools for that, we make a simplifying assumption. Now this is just an assumption. Suppose mu is a function of only one variable, okay? Let's say x, okay? So that mu sub x, this one, is equal to d mu dx, okay? That makes mu sub y 0, okay? And that makes mu just a function of x, okay? If that works for us, then the d mu dx, what we have here, and this term is 0, so let me bring this up to the top. D mu dx, okay, now this is now assuming mu is a function of x alone, okay? So this is equal to, well, I'm going to leave my n in there for just a moment, okay? They skip it, but I would think it's helpful to show it. Times n, okay, is equal to m sub y minus n sub x, which you already know, times mu, okay? Then divide both sides by n. Okay? And that gives you what we have as example, as equation 10. Okay? Now we're still at an impasse if m sub y minus m n sub x divided by n has a y in it, okay? If they depend both on x and y. However, after all obvious algebraic simplifications are made, the quotient turns out to depend solely on x. If that happens, then 10 is a first-order differential equation. This would be a first-order differential equation. If all this right here is a function of x alone, and you know mu is, and d mu dx is, so if that's a function of x alone, we have a differential equation, a fairly simple differential equation. Well, how simple? Okay. An ordinary differential equation. We can finally determine mu because mu is separable. Okay? If all this depends on x alone, then you can say d mu over mu is equal to all this mess, m sub y minus n sub x over n times dx. Okay, just write it in differential form. And if all this depends on x, which was our assumption here, all this depends on mu, which it is, this says that the log of mu, maybe absolute value, I'm not putting that in yet, is equal to the integral of this, m sub y minus n sub x over n, which we're assuming is a function of x alone, dx. We'll then take an exponential of both sides, and you have mu is equal e to the integral of m sub x and m sub y minus n sub x over n dx. Okay? Now, that works if this difference is a function of x alone. If it's not, try this. Do everything else with respect to y, and then you're going to come up with n sub x minus m sub y over m. If that's a function of y alone, then you're okay too. It's the same form, everything else is the same, except mu is a function of y alone. Okay? So if either one of those will work, you've got it knocked. If they don't, there's no hope. I mean, not in this method. So hang it up. Okay? So what we're going to do is example 4. Okay? Now I can't keep this on the screen. I don't have enough room. But let's go on and delete that and do example 4. Here's a nonlinear first-order differential equation. X, y, dx. Okay, so far. Plus 2x squared plus 3y squared minus 20 dy equals 0. Now there is a differential. We've been calling them all differential equations. That's in differential form. Okay, what's our test? Say that again. Okay, and how do you do that? Partial of xy with respect to y, and what would that be? X. Okay, what do we do here? Partial of all that mess, I'm not going to write it all down, with respect to x, and what does that give us? Say again? A little louder. Okay, this is respect to x. 4x. That's it. Because the y is counted as a constant, the 20 is a constant. Well, the bad news is x is equal to 4x, okay? So that's not an exact differential equation. But the good news is that x and y, I mean this thing here and that thing there, m sub y and n sub x are both a function of x alone, okay? Now, the n, though, has a y in it. That's a mess, okay? But let's see if there's anything we can do to fix that, you might say, okay? So what we're going to do, because those are both functions of x's, okay, what we're going to do is use equation 13. Can you see that in your thing? That one. That's going to be what we attempt for our integrating factor. Okay? We're going to attempt to do mu of x is equal to e to the integral of m sub y minus n sub x divided by n dx. Okay. Now, this thing needs to be a function of x alone. So let's see what that thing is. M sub y is this thing. X minus m sub x, n sub x is that thing, 4x divided by n, which is 2x squared plus 3y squared minus 20. That doesn't look very promising, does it? Okay. Let's work with it and see what we got. This will be minus 3x over 2x squared plus 3y squared minus 20. Okay? That depends on both x and y. So our first guess there, which seemed the obvious guess, isn't going to work. Okay? I don't know why they had us write it out, but they did. But let's do it the other way. The n sub x, let's try it this way. Mu of y equal e to the integral of n sub x minus m sub y over m dy. And let's see what happens there. Okay? Well, let's do that. That would be, n sub x would be 4x over, let's just do minus x, okay, over m, which is xy. Okay? Uh-oh, look at that. What does this become? 3x over xy, which is 3 over y. Would you believe it? Even though it looks like we had promise for x there, we didn't. You couldn't get rid of the y in that. But when you did it the other way, which didn't seem very promising, sure enough, you did eliminate the x and you have a function of y alone. So now your integrating factor is mu of y now, function of y alone, is e to the, oh, we've got to integrate this. Let's integrate this dy. And what does that give you? Three times the log of y. I guess you technically should put that in absolute value. Okay? Which you could write that is ln of y cubed. I don't know if that's any better. And so that's the integral of that. And when you raise e to the ln of y cubed, e and ln wipe each other out, so this just gives you y cubed. Now, can you drop the absolute value thing? They do, They don't even put it in ever, okay? So all you have to do is watch out that y is never negative. If y were negative, you're in serious trouble. This won't work. But if y is always positive, you're okay. Okay, so since you have that, go back to your original problem, and that now becomes xy to the fourth dx plus 2x squared y cubed plus 3y fifth, right, minus 20y cubed dy is equal to 0. You've just multiplied everything on both sides by y cubed. Okay? Do you want to do your test again? Let's just do it for fun. What's the partial of this with respect to y? 4xy cubed, right? Take the partial of this with respect to x, and what do you have? Plus 0 plus 0. Yes, look at that. They do work, okay? So now, that's just to get it so you can do it. Now we got all our work cut out for us, okay? Now, remember? Okay, I think I'm going to erase everything except that last little bit, okay? I don't think we need that anymore because we've modified it. Don't think we need this anymore because that didn't work anyway. Don't think we need that anymore because that didn't work anyway. We'll erase this. We did use it, but it worked out and we've got our answer. So we'll erase these. Okay. We've already used our integrating factor. And that took care of this and that. And that. We've used all that. So here's our differential equation. Okay? Now, how do we proceed from there? We want this thing here to be the partial of f with respect to x. To be xy to the fourth. Right? Because that's what that would be, okay? Now, let's integrate with respect to y. Well, this is just f of xy would equal, and what's that with respect? I said, hey, why did I do that? Dx, okay? And what would that be? X squared y fourth over 2 plus some function g of y alone. Right? Okay. Now we'll take that one and take the partial of this f with respect to y. And what does that give us? Two x squared y cubed. No, you're doing with respect to y. Second? We're taking the derivative. Yeah, this is a partial of that thing with respect to y. We're swapping back and forth so frequently it's easy to get confused. So that would be a 4 times 1/2 would be 2. X squared is counted as constant, and the y reduces to by 1. So that. Plus g prime of y. Okay? Well, let's see what our thing here is. This is exactly that, isn't it? So this yields g prime, well, I'm going to write it right, dg dy, flipping my notations as needed, is equal to 3y to the 5th minus 20y cubed. Okay? And if you write that in differential form, then integrate, this will be g of y is equal to what? You're integrating both sides of that. You came up with the g prime of y. See, this one wiped out that term. Okay? G prime of y was just dependent on y alone, so we wrote it down like that. G prime is dg dy is equal to that, and then write it in differential form with the dg here and the dy there. You integrate dg and get g. Integrate that with respect to y. You always got it y. So what was that? Okay, say a little bit like, okay, they'll give you, yeah, 3y to the 6 over 6. Is that what you said? Okay. Minus 20. Okay. And we'll have a plus c. We'll take care of that in a minute. Here, that goes to being 1/2. Here, this goes to being a 5. So this winds up being 1/2 y6 minus 5y4. Okay? Plug that back in here, and your f of xy is equal to x squared y4 over 2 plus y6 over 2 minus 5y4, and that's all equal to your constant c. Okay? This wasn't a boundary value problem, so we don't have, or initial value problem, so we don't have anything to go off. Let's see what we got. 1/2 x squared y4, I wrote the 2 under it, but it's fine, plus 1/2 y6 minus 5y4 is equal to c. That gives you your family of solutions. Okay. Now, remarks. When testing an equation for exactness, make sure it is the precise form mxy dx plus nxy dy equals 0. Be sure you have that plus sign in there, okay? Otherwise, you could screw some things up and think it's not exact. That's why I manipulated that 1 and reversed the signs to make that a plus, okay? Sometimes a differential equation is written as g of xy dx equal h of xy dy. In this case, first write g of xy dx minus h of xy dy equals 0. Then identify m of xy as g of xy and n of xy as minus h of xy. You have to have it exact with the plus sign in there. Okay. And the second remark here, in some texts on differential equations, the study of exact equations precedes that of linear equations. Then the method for finding the integrating factor just discussed can be used to derive the integrating factor for a linear differential equation by rewriting the last equation in the differential form of p of x times y minus f of x dx plus dy is equal to 0, and then your m of y minus n of x over n equal p of x, you're already there. So that's if you did it in the other order. We haven't, so it's fine. Homework exercises. Do some of the odds 1 through 19. There's a whole bunch of them there. Do some of them. Then do some of the odds 21 to 25. Okay. Do 27. That's the only one like that. Do 29, the only one like this. Do any of the odds 31 to 35. Do 37 and do 39. You can look at the rest of them. I don't think those have answers in the back, but you can look and see. And by the way, research papers. In this class, I haven't gotten any in yet, okay? which is okay, but be sure you don't let it sneak up on you, okay? You only have basically less than a month left, okay? So don't let many weekends go by that you don't work on that. All right. That's for you too, Marcus. I know you're not here. I hope you're listening. Okay. Okay. Now, we're ready for 2.5, which is solutions by substitution. Okay? So let's clear the screen. Okay, this is what I wanted to do. Okay. Any questions on 2.4 before we leave it? All right. Now, 2.5. We usually solve a differential equation by recognizing it as a certain kind of equation. Separable, always check that first. Those are the easiest. Linear, check that. Exact, so on. Then carrying out a procedure consisting of equation-specific mathematical steps, say separating the variables, integrating, yields a solution for the equation. But it is not uncommon to be stumped by a differential equation. Let me repeat that. It is not uncommon to be stumped by a differential equation because it does not fall into one of the classes of equations that we know how to solve. The substitution procedures that are discussed in this section may be helpful in that situation. Often the first step in solving a differential equation consists of transforming it into another differential equation by means of substitution. Now, what we were just doing with integrating factors, that's a transformation. It's not the substitution, though. So we're going to do it by substitution. For example, suppose we wish to transform the first order differential equation dy dx equal f of xy by substitution of y is equal to g of xu, where u is regarded as a function of the variable x. If g possesses first partial derivatives, then by the chain rule, now this is a bit bizarre, but here's what we've got. Now this is all literal now, so it might not make tons of sense like this, but it'll hopefully come out in the wash, okay? Here's what you had. A differential equation, dy dx, there's your derivative, is equal to some function, f of xy. And this has stumped you on how to solve that, okay? Separation of variables doesn't work, it's not linear, and it's not exact. And you can't think of an integrating factor that makes it exact. So our substitution would be let y equal g of xu, okay, where u is regarded a function of the variable x. Now, where u is a function of x alone, okay? So g is a function of x and u, but u is also a function of x, okay? Which seems a bit bizarre, okay? Now, if that g possesses first partial derivatives, then by the chain rule, dy dx would be partial of f with respect to x dx, I'm writing it out in gory detail, plus the partial of f with respect to y dy dx, okay? But that would be if you use the f. We're not using the f, I'm sorry. We're using the g. So let me change this. Okay. Let's go back. Okay. We're using y is g of that. Okay, so that would be partial of g with respect to x, dx dx, plus the partial of g with respect to u, du dx. Okay, that's what I meant to write. Okay. Now, this is 1. So this is going to be the the derivative of y with respect to x is equal to g sub x, okay? Partial g with respect to x, it's still a function of x and u, okay, plus the partial of g with respect to u, du dx, okay? This is x and u, can't write, du dx, okay? And that's a derivative, not a partial. Okay. Okay. If we replace the dy dx, which you have there 3 times, by the foregoing derivative, okay, that would be the right-hand side there, and replace y in f of xy by g of x and u, then the differential equation at the very top, dy dx is equal to f of xy, becomes the left-hand side of that becomes, this becomes g sub x of x and u plus g sub u of x and u du dx. Okay, that's the left-hand side. The right-hand side is your f of x. Okay, except we don't do f of xy, we put it f of x. And then y is g of xu. Okay. That sure is making a lot of sense, isn't it? Seems like it's all just sort of, it's all right, but you think this is making it simpler? It looks like more complicated. Okay, now, what we want to do is solve this for du dx, okay? So basically, what we've got then, we're going to subtract a g sub x, xu, from both sides. Okay, that wipes that out. And then divide everything by g sub u with respect to x and u. Okay, and that will wipe out that. Okay. Okay, so now we have what du dx, that's that thing, is equal to some big function f, is just a function of only x's and u's. There's no y showing up anywhere in the thing. So this thing on the right, we're going to call some capital F of x and u alone. Okay? Now, if we can come up with a solution of that differential equation, this one right here, that's easier than this one was to begin with, okay? Let's just say that solution would be, cord all wrapped around my ID, okay. That's going to come up u, okay, and this needs to be a function of x alone, remember, that was our assumption, is equal to some solution function phi of x, okay. That's going to solve that, if it's solvable, okay. Phi is a function of x alone. U is equal to some phi, which is function of x alone. Okay? Then the solution of the original equation is y is equal to that g function, whatever it was, of x and phi of x. Okay? It seems like round and round we go. Where we stop, nobody knows. Okay? Now, in the discussion that follows, we examine three different kinds of first-order differential equations that are solvable by means of substitution. The first one is going to be a homogeneous equation. The next one will be Bernoulli's equation, and the last one will be reduction to separation of variables. Okay, and I've got to sneeze. I'm sorry. Okay, sorry about that. Yeah, I think I'm going to have to go clear my head a little bit. Do you mind a very quick break? Okay, we'll pick. All right, let me say that again. Sorry about this. There's two types of homogeneous differential equations. When we get to higher order differential equations, we'll say it's homogeneous if everything's equal to 0. That's not what we're talking about here. We're going to do that next chapter. Okay? This is a different kind of homogeneous equations, and here's what we mean by this. Let me erase what we've got here, and let's do that. If you have a function f that possesses this property, that f of tx, ty, okay, is equal to t to the alpha f of xy. Okay, we're still in symbolic la-la land here. I mean, what in the world is that meaning? Okay. For some real number alpha. For some alpha. Call alpha. Okay. Then f is said to be a homogeneous function of degree alpha. Okay. All that blah blah, here's what an example is. And it's pretty simple. F of xy. Here's your f of xy, is equal to x cubed plus y cubed. It's a homogeneous equation of degree 3. Okay. Now, what all this ty and t to alpha, I don't know why they phrase all that. If you can write the equation and your x's and y's are the same power, it's a homogeneous equation. Okay? Now, and here they show this. F of tx, ty is equal to, well, if you plug that in, that would be t cubed x cubed plus t cubed y cubed, right? You cube what's in the first, you cube what's in the second. And this is equal to t cubed times f of xy, which is x cubed plus y cubed. So there you have met the criteria, and this says that it's homogeneous of degree 3. Okay? Now, how about this one? Alpha of xy is equal to x cubed plus y cubed plus 1. Is that homogeneous? No, it's not. Okay, because this term is not got a variable to the third degree. Okay, if you were to do f of t x and f of ty, that would be t cubed x cubed plus t cubed y cubed plus 1. Because there's nothing that you can put in there. You can't factor out t cubed and get your f of xy. This term is not to the third power. Okay. Now, the first is a pretty simple, obvious one. This one, once you get used to it, is not to the same, so it can't be. Okay. Now, let me, I'll continue on this page, okay? What do you have a first order differential equation in differential form, which is m of xy dx plus n of xy dy is equal to 0. Well, that's a differential equation in differential form. What I would do first is see if partial of m with respect to y is equal to partial of n with respect to x. If it is, it's an exact differential. But what if it's not? Okay? Or even if it is, it's said to be homogeneous if both the coefficient functions m of x, and n of y, m and n, they're both of x, y, are homogeneous functions of the same degree. Okay? In other words, if that is homogeneous, if this is homogeneous, if m of tx, ty is equal to some t alpha of m of xy, okay? And n of tx, ty is equal to t alpha n of xy, okay? Now, not just that, the alphas must be the same, okay? They've got to be the same, okay? Now, I knew I should go to a new page here, but all right. If they are the same, m and n are homogeneous functions of degree alpha, we can also write, now this is not as obvious, m of xy, that coefficient function of your differential form there, that m of xy is equal to x to the alpha, m of 1u. Okay? Now that came from nowhere that I can determine. And n of xy can be written as x, as, say x and write alpha. Okay. I believe it's y to the, no, it's still x to the alpha, n of 1u. Okay? Where u is equal to y over x. Okay. Now, not just that, but m of xy could also be written as y to the alpha, m of v1, and n of xy can be written as y to the alpha, same alpha, n of v1. Okay? But this time, your v is equal to y over x. I mean, x over y. Okay? Okay. Okay. Now, they refer you to the problem 31 coming up in this problem set later. If we get that far, you can go for it, okay? And basically, either of the substitutions, if you look at this one, the first one here, that substitution would be y is equal to ux, and this one would be x is equal to vy. Okay? Either one of those substitutions could produce if it's a homogeneous equation, these will produce new dependent variables and will reduce the homogeneous equation into a separable first order differential equation. Okay? It says to show this, observe that the consequence of that second one there, a homogeneous equation it just seems like more of the same here. Okay. We've only got a few minutes. We don't have time to do example 1, so let me just write a few more lines here. I'm out of room at the bottom of the page. I was probably not going to finish this, but I'll at least get it started for you. Okay? Let's start with equation 2, that m of xy is equal to some x to the alpha times m of 1 u. N of xy is equal to some x to the alpha of 1 u also. Okay? And where u is equal to y over x, which of course implies y is equal to ux. Okay. Now, if these are homogeneous equations, the m and n are both homogeneous, same degree alpha, then you can rewrite this as this equation here, okay? Actually, go back and write your differential equation, I think. M of xy in your differential equation would be this thing, x to the alpha m of 1 u dx, because it was m of x dy dx, plus your n of xy is x to the alpha, whoops, I left off the n here, n of 1 u, okay, dy, okay? That's how you would write your differential equation, and this, by the way, is equal to 0. Okay? Now, because x to the alpha is some non-zero number, it's a factor in both of them, divide them out. Divide into 0, you get 0, okay? And remembering that u is equal to y over x. Okay. Which also implies y is equal to ux. Now, by substituting, and let's do dy is equal to u dx plus x du, okay, into the last equation here. You see, this has no y in it, okay? This has no y in it, yet we have a dy there. Now the x's, you still got x's there because u is a function of x, so that's okay. You don't have y's, so if you put this in for the dy here, what you have now is m1 u dx plus n1u times u dx plus x du equals 0. Now let's get the dx's together. Okay, that would be m1u plus n1u times u dx plus n1u x du. That's equal to 0. Now they probably haven't written it quite the way I did. They wrote this u up here before the n. That makes it a little clearer. And they wrote this x before the n. But that's exactly what they've got written there. Okay? Now you can separate variables. Now that you got variables x's and u's. This is a function of u alone. This is a function of x alone, basically. Well, kind of. Okay? So, if you divide both sides by x, okay, that wipes out there, and divide both sides by m1u plus n1u times, or un1u, okay. Then what you have is dx over x plus n1u over m1u plus u n1u du is equal to 0. And that is separated. Okay? Okay. We'll hold off there. That's just, we're out of time, past time. So we'll start with example 1 next time. Now, since we haven't done any examples here, probably going to have a little bit of a problem doing any of the homework exercises. If you want to look at some of the 1 through 9, you can. I would say just wait. Do the 2.4, and we'll get to the 2.5 exercises next time. Okay? Any questions? I know we haven't hit a number in ages here, except the number 1 and 0. Okay? And this isn't a binary system. So we will actually do an example at the first next time. Good deal. Any questions?
I left my test 1 at home, but I did finish it.
Okay.
So I'll have it Tuesday.
Okay, that'll be great. Yeah. Okay. And as far as I know, we will have class 2 days next week. So, okay. I sure hope so anyway.